So we're going to start with the unsaturated hydrocarbons, and that's going to be our alkenes and alkynes. So I'll start just with alkenes. So these are hydrocarbons. So they're molecules made up just of carbon and hydrogen, and they have at least one double bond. Between two carbon atoms. So those carbons are sp2 hybridized. And so in general, their structure or formula is going to be Cn and then H2n, which is like our cyclic structures when we covered alkanes. So we've lost the extra two hydrogens, and when we're making the double bond, we have to take a hydrogen off of each carbon in order to do that. So a nice easy example would be ethene, right? So we have a carbon, we write it like this. Looks like there might be a double bond between the H2 and the C, but that's sort of just how we write the condensed formula. But we know that the double bond is actually between the two carbons. So if we want to expand the structure, we have our carbon-carbon double bond, and then each carbon is bonded to two hydrogens, and theta here is 120 degrees, right? The electron geometry is trigonal planar. That's going to be a big deal to us later on. When I tell you that something is sp2 hybridized, it's like I'm saying, hey, this is flat. So remember, we have a double bond here, and this double bond is made up of 1 sigma and 1 pi. Right? It's not 2 sigma bonds. So keep that in mind. The pi bond is not nearly as strong as the sigma bond. The orbital overlap is not as great. Remember how we drew that picture? You can go back to look at the hybridization video in the general chemistry review. We have different types of alkenes, and here we'll get into nomenclature in a sec, but I'll name this under this molecule just to get us started here. There's two ways. Remember, we talked about in alkane nomenclature, we have IUPAC. This is where we're going to take the prefix for however many carbons are in the structure. So we see 2 carbons in the structure. So this is an eth, and we're going to use the suffix ene to let someone know that there's a double bond. In this molecule, we don't have to get specific about where it is because there's only 2 carbons in the entire molecule, right? And then we talked about how there's a different type of nomenclature, a different set of rules, or a different system. Sometimes we use what's called a common system. And this is for molecules that are sort of, used all the time, or they're pretty, in other words, common to certain folks. And the naming is a little different. So for this molecule, it would be ethylene. So in common nomenclature for these hydrocarbons, they're going to take whatever your alkyl group was, and then plop the suffix for whatever functionality you have. So with unsaturated hydrocarbons for alkenes and alkynes, the double and triple bond are going to be our point of functionality. It's finally a spot where we can actually do some chemistry, right? So alkanes, not so much chemistry going on with those, but with alkenes and alkynes, we have pi bonds that we can work with, right? They're easier to break than sigma bonds. They're weaker, their orbital overlap isn't as great. So in essence, we can use them as a source of electrons, and that's going to be important to us coming up. The different types of alkenes. So we have them in classes because we say that for a molecule that has at least one double bond, you have an alkene, but you can have more than one double bond, right? So in some instances, you'll have a molecule where you have a couple, but they're isolated. And so an isolated alkene will be something like this, right? Where they're not right next to each other and they're not every other bond. So in other words, you have double bonds, but they're all alone, essentially. In their spots on the molecule. And we'll go into why that matters when we get into reactions. The second one is where you have cumulated, so one right after the other. So I could have something like, remember when we were talking in just the general chemistry review and we introduced functional groups, I said you could put a little dot there to indicate that there's a carbon. When you're doing a line bond structure, right, so this could go on and on, whatever, right? So it's one right after the other. And the third type, and this is going to be the interesting kind that we like to use for some of our reactions, is conjugated. And this is every other carbon bond will have a pi bond. So like that, right? Something like that. So every other carbon bond will be a double bond. With alkynes, we have similar situation, but we have triple bonds instead. So this is going to be at least one triple bond between two carbons. Your carbon is sp hybridized. So you'll have 1 sigma and 2 pi. So in general, we've got Cn and then H, 2n minus 2. So for example, we'll keep it to 2 carbons. we have ethyne. So over here, try to keep it consistent with the colors. We have IUPAC nomenclature, where we're going to use our prefix to indicate how many carbons we have. And so we have eth. Then we're going to use YNE to let someone know we have a triple bond. So that's the suffix for an alkyne. In common nomenclature, annoyingly, some of the smaller alkynes are named using the alkene suffix. And we'll use the common sort of prefix to indicate however many carbons there are. And those common prefixes actually come from carboxylic acids, common carboxylic acids. And the carboxylic acid that only has 2 carbons is acetic acid. And so we're going to use the acete prefix for this, and then we're going to put "ene" on the end of it. So common nomenclature with alkynes can be a little confusing, but it is a very common molecule. This is called acetylene. Either of those names is fine. So there isn't one sort of system preferred over the other, but for certain molecules, the common name is more commonly used. And I'm sure some of you have heard of acetylene. It's a component of rocket fuel, right? Not too many people call it ethyne, but that is its IUPAC, or in other words, its systematic name. With the triple bond, so if we expand the structure, we have a sigma bond between the hydrogen and this carbon, and then we have a triple bond here, which is a sigma. So 1 sigma plus 2 pi bonds. So each one of those carbons is sp hybridized, right? There's a sigma bond between the hydrogen and the carbon, a sigma bond between the 2 carbons, and then 2 pi bonds. So we only needed 2 hybrid orbitals in order to make those sigma bonds. The 2 unhybridized p orbitals are used to make the pi bonds. Again, if you want to go back and look at the hybridization video in the Gen Chem review to help out with that, you can. Speaking of the different types of bonds, so just a quick mention of our bond energies, because when we get into reactions with these, it's going to matter which one was easier to break, which one was, gave off more energy when it was made, which one gave off less energy, that kind of thing. So those will be the strength of the bonds. We remember that the single bond is just a sigma bond, right? So a single bond is going to be greater in energy, or I'm sorry, the sigma bond is greater in energy. A single bond is less energy than a double bond, because a double bond is 1 sigma plus 1 pi. This is 1 sigma, and that'll be less in energy than a triple bond, which is 1 sigma and 2 pi bonds. So the pi bonds are lower in energy, right? They're weaker than sigma bonds, but we've got a sigma plus 2 pi, right? So the triple bond is going to be shorter, and it's going to be higher in energy, and it's going to be harder to break, right, than a double bond, which is going to be shorter and harder to break, or higher in energy than a single bond. When we do chemistry with alkenes and alkynes, we're actually doing chemistry with the pi electrons, right? Those unhybridized p electrons, because those bonds are weaker. They're easier to break. So we're going to use these molecules as a source of electrons. Just like we had in the alkanes, we can make isomers of these. This might be a little easier to see. We have 2 different ways to describe it. I'll start with our cis-trans isomers. So just like we talked about with cis-trans isomerization with rings, so cycloalkanes, where you have two groups that are either on the same side of the ring, same face, right, above or below, or on opposite sides. With alkenes, so we don't really have these with, I should put alkenes. We don't have this with alkynes because they are 180 degrees, the bond angle. But with alkenes, let me go back up here and do that for you. This bond angle, theta, is 180 degrees, right? So there's a linear molecule. So we don't have this sort of same side, opposite side of the functionality. The triple bond, right? It's just linear. But with alkenes, since it's a 120-degree bond angle, we do have this opposite side, same side of the double bond situation. So if you have an alkene where you have two groups, like two methyl groups, for example, on opposite sides of the double bond, we consider that to be a trans isomer. Remember, the hydrogens are implied, right? So if I want to say, hey, let's put chlorines on here so we can see the difference. And if we want to write the hydrogens in, it might make it a little more obvious. Versus if we had a double bond and we have our chlorines on the same side. We have a cis configuration. And you might be sitting there going, well, who cares, right? Well, actually, this affects certain physical properties. It also can affect the chemistry that we can do on a double bond. The outcome of the chemistry we do on the double bond is affected by what this molecule actually looks like and how it's put together. With the trans isomer, we have a situation where, and I can draw these in for a sec if you like, we have a dipole moment going in opposite directions here, whereas on the cis isomer, these are going to add together. So your cis isomer is going to be more polar, and that's going to affect some of its physical properties. So for example, the cis isomer is going to have a higher boiling point than the trans isomer, right? So these different isomers are going to matter to us when we get into doing chemistry with these molecules. This is a situation where you have a simple molecule, right? And you have two carbons. Each carbon has a hydrogen and then something else on it, right? And that something else is the same. So we can say that those two different atoms, or in other words, those heteroatoms, are either on opposite sides of the double bond or same side of the double bond. But what happens when you have more than two different groups on the double bond, right? So what happens if one carbon has like a methyl group and a chloro group and the other, has like just a methyl group or whatever, right? So what if you have like a combination of different functionality? Then it's not just simply a cis-trans isomer anymore, because now you're like, well, which groups are you talking about, right? So if I have a situation where I've got more than two different substituents, or I should say, two or more groups on the alkene, for example, if I have something like this, like I'll take a methyl group, we'll bond it to a carbon that's doubly bonded to another carbon, and we'll say this carbon has a methyl group and an ethyl group. Now I can't tell you that's cis or trans, because you'll sit there and be like, well, are you talking about the two methyl groups, that those are cis, right? Or if you're talking about a methyl group and the ethyl group, those are trans, like, so when you're naming it, you need a way to let somebody know what isomer you're talking about. So we're going to have a look at the carbons that have the double bond between them, and then we're going to look for the substituents on those carbons and find the biggest ones. So we find the biggest substituents on the carbon on the left is going to be the methyl group, and the biggest substituent on the carbon on the right is going to be the ethyl group. So in this situation, we have the two biggest groups, and these are going to be across from each other. On the double bond. So you would say normally, hey, that's trans, but you can't really say that because there is another methyl group, right? So it would be like, well, are you talking about the two methyl groups or are you talking about the methyl and the ethyl groups? So we have a different way of naming these. We're going to call this E, capital E, when they are not the same group. If, for example, I have a molecule where I've got, say, an ethyl group on one side, so here's my double bond, and I guess we'll just put our hydrogen down here again. We'll put a methyl group down here, and we'll put something bigger over here. Say we have like an isopropyl group. So now we look at the two carbons in the alkene, and we're going to find the biggest groups on each of those carbons. So in this case, they happen to be on the same side. So two biggest groups are going to be on the same side of the double bond. And so when they're not the same group, we're going to call this the Z isomer. These come from German words for, across from or on same side, or you know what I mean? So these letters come from German words. I can totally understand why the Z looks like it should be the across from, right? Because a Z actually kind of looks like a trans isomer, but the letters themselves designate the position of the groups relative to the double bond based on German language, right? Not just what the letter looks like. So if we're naming this, we would put a Z in parentheses and then start naming the molecule, right? For the other one, we would put an E in parentheses, kind of like if you were naming cis trans. You would italicize it or underline it. For E and Z, we typically put that in parentheses when we're writing it down. If we're typing it, we typically we use italics. So that's not really a hard and fast rule, but that's kind of how you would see it presented. So let's name some of these to get some practice. So naming an alkene, we're going to treat the double bond, or even just an alkene or an alkyne. I'm going to start with alkenes, but naming these things, we're going to start with the functionality. So you're going to treat the double bond or the triple bond like it's its own functional group. So when you're naming these and numbering them, when I say give it priority, I mean give it the lowest possible number. So in other words, they are the most important piece of the molecule, if these are the only pieces of functionality on the molecule. So they will be most important. So again, an alkene suffix is going to be -ene. And we'll use a prefix to designate how many carbons. Alkyne suffix will be -yne for IUPAC nomenclature. So let's give this a try with a few examples. Easier to just see it than to talk about it, right? You're going to follow the same rules that you followed for naming alkanes. So the first step is to find the longest continuous chain of carbons, right? So say, for example, all right, so we can name these by counting in either direction. So we've got 1, 2, 3, 4, 5, 6. Or I could count in the opposite direction. I could go 1, 2, 3, 4, 5, 6. If I went up into that methyl group, I would only have 5 carbons. So my longest continuous chain is 6 carbons. So that's going to be some kind of hex, right? But it's not a hexane, it's a hexene, because I have this double bond here. And that's going to be my functionality. So that's going to be, it's not a substituent like that methyl group is, right? Or if there was like a chloro group or a bromo group or whatever. So this molecule is actually named after the alkene. So I'll be using that suffix. The other thing you want to do is then to make sure that you're going to be giving the double bond priority, right? So you're going to want to let somebody know which carbons bear the double bond. If I go from left to right, then the double bond begins on carbon 4. And if I go from right to left, then the double bond begins on carbon 2. So I'm going to number this from right to left. So then I'm going to get rid of these numbers down here because I want to show you something else. On those carbons, not written in but just implied, are hydrogens. So you have to let someone know what type of isomer you have here. And this is where we would use EZ, right, nomenclature, or cis-trans. So in this particular case, we're going to use cis-trans because both of those carbons have 2 different substituents. They also each have a hydrogen. So I'm able to tell you that this is a trans isomer because those different groups are on opposite sides of the double bond. The other 2 atoms that are bonded to each of the carbons, right, the other the other atom bonded to each of the carbons, I should say, is a hydrogen. So we don't need EZ nomenclature. If we had like some other group on one of those carbons, we would need EZ. But in this case, it's just two different substituents. So we're going to call this the trans isomer. So we write trans and then a hyphen. And then you have to start telling people where you see substituents. On this molecule, I see that I have a double bond between carbons 2 and 3. And I see there's a methyl group over here on carbon 4. So I'm going to write 4-methyl. It's the only substituent on this molecule. I have to then let you know where the double bond is. It begins at carbon 2. So 2 dash. There are 6 carbons in the whole parent. So hex. And that 2 stands for a double bond. So -ene is the suffix that we would use. So if you want to pick this apart, you can. You could say that you have an alkene, and there's only one, right? One double bond, so we don't have di or tri or anything in there. It's just one double bond. The parent has 6 carbons. This is where your double bond is. So it's between C2 and C3, but we're going to give this functionality priority, and so we're going to give it the lowest possible number. We have a methyl group. This is a group on C4, and this is the isomer that we have. So in other words, we have the two biggest groups, in other words, not the hydrogens, right, on opposite sides of the double bond. And I know that sounds confusing because we didn't name that thing as a group, but it's the rest of the molecule, right? So you could view it as R. We have a methyl group, right, the rest of the molecule on the right-hand side, and then the rest of the molecule on the left-hand side. They're on opposite sides of the double bond. If it's easier to see, you can draw the hydrogens in, but we typically don't see these written in. So see that? This would be like if you wanted to write this out differently. You could be like, I've got CH3, CH2, CH, CH3, CH. Oh, hang on. I want to show you the double bond, the whole point of this. So this will be a group. Here's your double bond. There's the hydrogen. Up here, hydrogen. Down here, methyl. So that would be like the condensed / expanded structure that corresponds to that line bond structure up there. So you can kind of see now that your groups are trans. Let's use a cyclic compound. We'll name one of these. Okay, with cyclic compounds, we're going to be numbering around the ring, giving the alkene or the double bond in there priority. In other words, you're going to have to give it the lowest possible number. When you're numbering these things and there's only one double bond in the ring, you're always going to start with the lowest possible number, so number 1, and then you're going to number or name your substituents as you go through the double bond. So you're going to number through the double bond, giving the double bond the lowest possible number, while letting each substituent get its own lowest possible number after that. So you have to prioritize how you do this. So in this particular case, I could go like this. I could go 1, 2, 3, 4, 5, or I could go 1, 2, 3, 4, 5. So if I take the blue pathway, the methyl group is going to be on carbon 2, and the bromo group is going to be on carbon 3. If I take the orange pathway, because remember, you're given the double bond priority. We're not looking at those substituents just yet, just a double bond. So that's going to be carbons 1 and 2 always, unless there's another double bond, right, in the ring. So if I take the orange pathway, the methyl group is on carbon 1, but the bromo group is on carbon 5. So 2 and 3 are going to be smaller than 1 and 5. So I'll get this out of here. And I'm going to name this 3. So again, now the substituents are going to be put in alphabetical order. But that bromo group is on carbon 3. The methyl group is on carbon 2. And remember, we're separating the words and numbers with hyphens. And then you have to let someone know you have a ring. So we use the prefix cyclo. This is all one word, by the way. Pentene. So it's a 5-membered ring. Pent. Ene tells somebody that you have a double bond. In this case, we're not going to say 1 cyclopentene. It's implied that if there's only 1 double bond in the ring, it gets the lowest possible number. So that double bond has to go through carbons 1 and 2, and so therefore you know where to put the substituents relative to that double bond on the ring. You can have rings that have multiple double bonds. This is not a course where I'm going to be giving you gnarly molecules, right? So we're good to keep it simple. Rings with, 1 double bond. Occasionally you'll see, chemistry that we'll do with these, double and triple bonds, and I will mention the name of the molecule, but I'm not going to ask you to name something super difficult. So a ring with 1 double bond is totally fine. You're not going to have a small ring with a triple bond. The bond angles don't allow for it, right? And we're not going to be naming gigantic rings, so don't worry about the alkynes for the cyclic compounds. We can name an alkyne, though. So we could have something like an acyclic molecule. So we indicate these carbons with little dots in the line bond structure. This bond angle is 180 degrees. They're a little annoying to draw. Again, we have a couple of different ways that we can number this. We can go left to right, 1, 2, 3, 4, 5, 6, 7, or I could go right to left, 1, 2, 3, 4, 5, 6, 7. So no matter what, you have a 7 carbon parent. So this is a heptine of some sorts, but you got to tell somebody where the triple bond is. If I go from left to right, my triple bond begins on carbon 4. If I go from right to left, the triple bond begins on carbon 3. So we're going to take the orange pathway here, because that gives our functional group priority, or in other words, the lowest possible number. If there were substituents on this thing after we figured out what carbon we're going to call, where the triple bond is, then you're going to look at the substituents, and then they get second priority in terms of lowest possible numbers. And you do want to give them the lowest possible numbers, but you're looking for the triple bond, or if it's an alkene, you're looking for the double bond first. If, by chance, you run into a molecule that has a double and a triple bond on it, we prioritize the alkene. So if you ever see a molecule that has a double and a triple bond, you're going to give the lowest possible number to the double bond. and then the lowest possible number to the triple bond comes second priority to that. But in this molecule, we only have a triple bond, and it's on carbon 3. So we put a 3, a dash. There are 7 carbons. That 3 is speaking to the triple bond, so we put an "-ine". So why don't we do one where we're doing like a condensed formula instead of line bonds, so you can see how those look too. So make something up here. Notice how as we're putting these double and triple bonds in, we're systematically removing a proper number of hydrogens, right? So those degrees of unsaturation are going to increase with more double and triple bonds. Carbon has 4 valence electrons, so we're not going to be violating that. Okay, so in this particular molecule, we have a triple bond. We also have a substituent. So we can number this from left to right or right to left. If we go left to right, we have 1, 2, 3, 4, 5. This would be carbon 6, 7, and then 8. If I go from right to left, I have 1, 2, 3, 4, 5, 6, 7, 8. So in this case, we numbering from left to right, so the blue pathway, we see that the triple bond, and if you need, I can highlight this so that it's easier to recognize in there. Our triple bond begins on carbon 3. If we number this from right to left, the triple bond begins on carbon 5. The only other different thing about this molecule is the methyl group as a substituent, but the triple bond is going to take priority. So the route that we take is going to be the one that gives that triple bond the lowest possible number. So I'm going to get rid of the orange pathway here, because if we take numbering from left to right, our triple bond is on carbon 3, and that puts the methyl group, so I can highlight that, make it easier to see, that puts the methyl group on carbon 6. So notice we're not giving this cis trans or EZ nomenclature. We don't have that with the triple bond. This is linear, right? So we don't have a situation where we've got bigger groups on opposite sides or same sides of anything. This is just straight, it's a linear geometry, right? 180-degree bond angle. So there's no cis trans or EZ isomerization with the alkynes. But we do notice that we have a methyl group on carbon 6, so 6-methyl. And then we have to let someone know where that triple bond is. So we're going to put the 3, and then we have oct, because we have 8 carbons in the longest continuous chain, and it's an alkyne, so -ine. And if you want to dissect this, here we have a triple bond. We have 8 carbons in the parent. This is where the triple bond is. And here you have a group. So your substituent is on C6. Let me show you one last example. Why don't we take an alkene where we've got a couple of double bonds. So keep it simple. So if I number this from left to right, I have 1, 2, 3, 4, 5. So longest continuous chain has 5 carbons. So that's a penta something, right? Or pent something. If I go from right to left, 1, 2, 3, 4, 5. So I have 2 double bonds. If I start naming this thing from left to right, the first double bond is on carbon 1, the second double bond is on carbon 3. If I go from right to left, the first double bond is on carbon 2, and the second double bond starts on carbon 4. 1 and 3 are smaller than 2 and 4, so we're going to take the blue pathway to give our functionality lowest possible numbers. So here and here is the start of our double bonds, right? So we have 1, 3. It's the same thing that you would do if you saw like 2 methyl groups, right? You're going to take the numbers and just separate them with commas if it's the same group. So we're treating it like it's a group, right? It is, it's a functional group. And then we're going to separate the numbers and the words with hyphens. So dash, you got to tell somebody how many carbons you have. So this is going to be penta. We put the in there for ease of speech. And we use the prefix di to let someone know there are 2 double bonds in the molecule. So this right here, we have 2 double bonds. The parent has 5 carbons, and the double bonds are going to be on C1 and C3. So this is 1, 3 dash pentadiene. So again, the A after the pent is in there for ease of speech. So that's going to do it for examples with structure and nomenclature. In the next video, we're going to hit some physical properties, and then I kind of want to jump into just a review, just a little, take a step back and just review a little bit of what we learned in general chemistry about reaction mechanisms. If you remember when you covered kinetics, you probably covered reaction mechanisms. So just want to draw a couple of reaction progress diagrams and sort of dissect what we're looking at in those, because as we move forward, we're going to be doing reactions with molecules that have functionality, starting with alkenes and alkynes, and there's going to be proposed mechanisms, or like, hey, how did this happen, or how do we think this happened based on data, right? So we'll take a little review of some reaction nuts and bolts kind of stuff, and then we'll talk specifically about different types of reactions of alkenes and alkynes.